Greetings, this is Purple Target, and welcome to my tutorial Let's Play KSP series, Krash Test Kerbals, Episode 1 Tac 3, How to Throw Kerbals at the Ground and Miss. We're currently using Kerbal Space program version 0.18.4. At Crash and Learn, we explore just enough rocket science to be dangerous, and learn how to abuse math instead of the other way around, to get our Kerbal out to the depths of space more or less where we want them for fun and profit, as opposed to just playing lawn darts with them. For today's objectives, there's a lot to cover, so I'll be rocketing through topics pretty quickly. Fortunately, there's a pause button totally within your control, so if you want to look at something a little longer than I leave it on the screen, you can totally do that. I won't tell on you or anything. So first up, we'll be looking at planetary rotation, make you aware of the motion of the ocean and everything else connected to it, and why anything we launch straight up will generally end up falling to the west of the Kerbal Space Center. We'll also be looking at specific impulse, which is a measure of the efficiency of rocket motors. So it's similar to with the cars and gas tanks, the miles per gallon or liters per 100 kilometers that you would measure on an internal combustion engine. And that'll lead us into delta V, or change in velocity. Delta V is a pretty important topic for a rocket, so we are going to spend some time on that, calculating the delta V for a rocket that we end up building, which is similar to calculating the range that you would get on a tank of gas for a car. And similarly, we'll take a brief look at how to predict the delta V required to get into orbit, since it's not quite as easy as just measuring off distances on a map. We'll also look at tangential velocity, try to say that 3 times fast, which is something that we can use to reduce the effective gravity drag. And when that velocity gets high enough, it becomes orbital velocity, which is how fast we need to go in order to miss the ground. Yes, we're going into orbit today. At least that's the plan. And we'll be taking a look at gravity turns, which is taking the going up part that we've been looking at for the last couple of episodes, and putting it together with the downrange part in order to get into orbit easier and more efficiently. And of course we all know that collecting underpants more efficiently means better profits. So we'll just flash 18.4 up here, and then we'll load our TAD-4 rocket from the last episode. The intention is to launch it straight up and watch the map view tell us that it's going to head for water to the east, and instead it'll come down on land to the west. And this is one of those tricks that you can totally try at home. The reason for this is that everything in KSP is moving. Even when our rocket is sitting on the launch pad at KSC on the equator of Kerbin, it's still moving at 175 meters per second eastward due to the rotation of the planet. You can actually check on this by looking at the nav ball and clicking on the velocity instead of where it says surface at 0 meters per second while you're sitting on the launch pad, or on the ground of any planet really. You can switch it over to orbit mode, and that'll give you a velocity relative to your orbit, or the center of the planet. It will be different than how fast the ground thinks you're going at any rate.
Checklist complete. Continue count. 10, 9, 8, 7, 6, 5, that's it. 4, 3, total set. 2, 1, mark. Clear the tower.
So as TAD-4 gets off the launch pad, we'll take a moment to talk about specific impulse, or ISP, which is simply a measure of efficiency of rocket motors, similar to how car engines might have miles per gallon or liters per 100 kilometers. So far, KSP doesn't have any sci-fi type engines like reactionless drives that run on magic space pixie dust. All the motors so far are similar to science fact reaction drives, which just means that they work by taking a reaction mass, generally in the form of fuel and oxidizer, and expel it out the nozzles at the back of the rocket in order to leverage Newton's third law of every action has an equal and opposite reaction. So the force given to the fuel mass while being pushed out the nozzles in the form of exhaust produces an equivalent force on the rocket that accelerates it forwards. So the actual force of thrust on the rocket is nominally equal to the reaction mass being expelled times the exhaust velocity, or VE, which is pretty much the same as our F equals ma equation, but with different letters. Same idea though. But in the meantime, we have an equation here that shows the relationship between exhaust velocity and specific impulse. and it's VE equals G naught times ISP, where G naught is the standard acceleration of gravity at Kerbal sea level, which is 9.81 meters per second square. So double the exhaust velocity and you can double your ISP. It's that simple. Now the full calculations for exhaust velocity involves a bunch of detailed math about nozzle design that is far beyond the scope of KSP or Krash Test Kerbals. It's not part of the game, so I'm not going to sweat it. However, we can see here as we look at the engine output for the LVT-30 engine as it ascends, that the ISP rating is getting bigger, i.e. more efficient, and the fuel flow is going down, while the thrust is being held the same. Because TAD4 is in an atmosphere, we have a bunch of air in and outside the nozzle trying to get in. So the greater the air pressure, the more it retards the exhaust velocity, because the exhaust has a bunch of air that it needs to push out of the way. Once we're in a vacuum, there's no longer anything impeding the exhaust, so that's where we see the highest and consistent ISP values for pretty much all the rocket motors. Now this also illustrates the three equations to the left, which is just the same equation for force of thrust, specific impulse, and fuel mass flow, or mdot, just written in three different ways. So we can see that ISP is proportional to the force and inverse to the mass flow. So if we double the velocity at which a motor tosses reaction mass out the back, we can see that it would double the ISP, or efficiency, which in turn would double the resultant force on the spacecraft. Or if the thrust was to be made constant, we would only need to use half the reaction mass to get the same force. Either way, the total mass of fuel on the spacecraft will allow us to go twice as fast eventually. So on takeoff, our spacecraft is still doing the same 10.5 kilometers per minute eastward. So when we look on the map, the predicted trajectory, as far as the orbit is concerned, shows a parabola that includes the lateral velocity of 175 meters per second eastward. And so of course at the end of that parabola, it tends to make a prediction for a wet landing. Now remember what I said about the motion of the ocean. It's not going to be there when our spacecraft comes back down again. So as I said, our origin is moving, so it's tracking along this yellow arc here at 10.5 kilometers per minute. So in a couple of minutes when our TAD4 comes back down, the ocean is going to have moved out of the way. So this may end up begging the question, why doesn't the spacecraft just come back down on top of the launch pad at KSP, since both the Kerbal Space Center and the spacecraft are both traveling at 175 meters per second, and after the same amount of time they should cover the same distance, n'est-ce pas? And the answer to that question is pi, or pizza, which follows the same rules as pi. Because we all know that the circumference of a circle is related to the radius and pi. And KSP is carrying on the original radius of 600 kilometers, as per Kerbal. So it travels along the little yellow arc. Our spacecraft is traveling along the white arc at whatever altitude the spacecraft ends up reaching. So while it's up there, the angle that it covers ends up being smaller. So the Kerbal Space Center at that lower radius ends up rotating underneath the spacecraft faster than it can catch up. As I said with pizza, you can actually try this with an experiment if you happen to have a small pizza hanging around and you can measure off a crust of like 3 or 4 inches or whatever your favorite size pizza is, and then measure off the same amount of crust on a larger pizza. And you'll find for the same amount of crust, you'll end up with a narrower slice on the larger pizza. And really, that should be all the incentive you need to conduct experiments when there's pizza at the end. Science is always better when accompanied by cheesy goodness. So there's some pretty heavy differences in how things behave in rocket science as opposed to how we're used to seeing them on the ground. And it's useful to try and get our Kerbal minds wrapped around some of these. For example, on the ground we might be used to going from one origin to a destination on a road or something like that, say if you're driving a car. And so we'll mostly think about it in terms of distance, the distance between point A and point B. And as we're driving along at a certain velocity, we have to keep putting energy in, in the form of gas or whatever, because if we let off the gas, the vehicle's going to come to a stop and we won't get to our destination. Well, in KSP things are a little bit different. Our origin and our destination are always going to be moving, and nothing is traveling in a straight line. The distance is not as much of a factor in rocket science. It doesn't matter how far away something is. If we're headed towards it, we're still going to get there because there's not much else out there to slow us down. So velocity is the new black. It really matters little how far away our destination is. What matters is how fast do we need to go in order to get there. And at the end of it, do we have enough gas in order to stop?
Splashdown. Negative contact.
And as predicted, TAD 4 is coming down to the west. As I was saying, our rockets in KSP don't care about the distance they need to go between A and B. There's no road friction or air drag to slow them down, so we only expend fuel when we're accelerating to go faster, or slower, or even change directions. It's the ultimate in cruise control. And we already talked about acceleration in the first episode, but even acceleration isn't that important. We need to worry about minimum and optimal amounts when we're needing to deal with landing and taking off from a gravity well of any planet or moon. But once in space, the acceleration just needs to be enough to get the spacecraft up to speed in a reasonable amount of time, which if you're patient can be minutes or hours or even days. Longer if you don't mind doing multiple orbits just to get the most out of burning near the periapsis. Our most critical factor in Kerbal science is delta V, which is simply physics speak for change in velocity. As we discussed with ISP, reaction drives depend on reaction mass in order to work. If you got no gas, you got no mass. Or is that the other way around? The point is that the rocket has to use its limited amount of fuel in order to change velocity. So if we had a rocket with 4,000 meters per second delta V, it could go from 0 to 4,000 meters per second in whatever time its little thrusters can take it. But that's it. It's going that speed until something else jumps out to stop it. Or it can go from 0 to 2,000 meters per second and then turn around to slow down again to 0. Or it can speed up to 1,000 meters per second and spend 2,000 meters per second goofing around changing direction, and then slow down by 1,000 meters per second, which may or may not be enough to stop at 0, depending on what it's been doing during the mucking about phase. Fortunately, someone gave us a simple equation to determine delta V, and that's the Tsiolkovsky rocket equation, or ideal rocket equation. And it reduces the problem to a simple logarithm of the mass ratio. So the original form is delta V equals exhaust velocity VE times the natural log of the total mass of the rocket, including propellant, payload, and the kitchen sink, over the dry mass, which is the mass of just the vehicle and payload, but where all the propellant has been used up and spit out. And of course we don't want to deal with VE really, because KSP gave us these handy ISP numbers, so we can sub in to make the equation equal to G0 times ISP times the natural log of the total mass over the dry mass. So whenever we're building rockets and planning missions, the rocket equation will tell us what the delta V our rockets will have. Then we can compare that to the delta V requirements of our mission. How fast do we need to get a certain altitude? How much to push through air drag? How much do we lose to gravity? How fast do we need to go sideways to get into orbit, or change orbits? How much to slow down again so that gravity, air, and parachutes can bring the Kerbals safely back to the ground? As long as we build a rocket that is capable of all these little velocity changes put together, then we should be able to achieve the mission. By the way, if you don't know about Tsiolkovsky, you should totally look him up. Like most people who leave behind funny math equations, he was a bit of a character. So today we're going through building the first prototype of a Kerbal Space lift vehicle, a light model that should be able to get a payload of 2 tons into orbit, although for the calculations we're just going to use what we actually have. So instead of a satellite, we'll just use a probe for control and an RTG for electrical power, and we'll call that the payload, and make note of the mass. This is trick number 1. Pay attention to your payload. It adds to the overall vehicle weight and all the stages below it. Then we're on to stage 1, which is the orbital insertion stage. This stage is primarily for the upper atmosphere or vacuum, and its job is to get the payload into a standard parking orbit. And for that I'm using 80,000 meters for Kerbal, so I have some room to maneuver lower without going into the atmosphere. I've generally set my parking orbits a percentage or some round number higher than the atmosphere or the highest mountains, whichever is liable to hit first. So we have a decoupler, which we're not going to use in this mission because we're not intending to place this particular payload into orbit, but this is going to be the start of a standard design. So it's here now because I will use it in later missions. I'm also putting some RCS thrusters on for attitude and roll control in space. Notice they'll only be at the front and away from the center of mass to maximize their effect. I'm not going to go sideways with this, it's just to control the nose when the probe body can't do it and the engine isn't running. And I'll put on some separatrons facing backwards, so if I use all my fuel putting this into orbit, I'll have a little something to get back out of orbit. When I do use this to launch satellites, this would fire to bring the spent stage back down to the ground after separation, so I don't leave up space junk. And there's parachutes to attempt a soft landing, so that we can possibly recycle this stage. It's not part of the game yet without career mode, but it's part of the Krash Test Kerbals rules. Minimize junk and maximize reusability. And then we add up all our components as usual, and we get the full mass and the dry mass for everything and sum it up. Now if you do add up these columns, you might notice a possible error in the total for dry mass. What's going on there? This is trick number 2. Not all mass is reaction mass, at least not for the main effort of the rocket. In red, we see the separatrons and the RCS tanks have dry mass listed, but we're using the full mass in the totals. That's because the RCS is for control, not speed, and the separatrons have a specific purpose of slowing the spent stage for deorbiting, so we don't count that into the dry mass. We only count the delta V from the 3 tons of mass from the fuel tanks that are actually being used by the main engine of this stage. So we have all our numbers and we start doing the summary for the stage. Remember, for the rocket equation we need to add the MP or mass of the payload to our total and dry masses. And we have to select an ISP value. Since this stage is for upper atmosphere maybe, but hopefully it really should be in vacuum, we will use the vacuum ISP value for the LVT-45 of 370 seconds. Now we can plug these into the handy dandy rocket equation and we get 7.43 full over 4.43 dry. Could be tons or kilograms, so it really doesn't matter. The equation doesn't care as long as it's the same units. We take the natural log of that ratio times 370 seconds for vacuum ISP times G naught, 9.81 meters per second squared, and we get 1,879 meters per second of delta V. Just a little prep work and common sense, and the rest is too easy. Now, stage 2 is the main lift module. Now its job is just to get up to altitude, so it's going to be working its way through the atmosphere up to where the insertion stage can take over. So it's just a simple bunch of fuel tanks with some parachutes for a soft landing. We don't need to slow this down because it's going to run out of fuel before we reach any kind of orbit, so it's always going to fall back to Kerbin. But we do need gimbaled engines just like the first stage so that it can steer itself during the burn. So trick 3, this is an example of serial staging, where one stage fires one after the other. So just like trick 1, we need to count the payload, but now the payload is the entirety of stage 1, including its payload. Any massive vehicle, payload, or fuel that this stage has to lift is just payload now, dead weight, that this poor thing has to lift. With trick 4, this stage has 2 engines. Double the engines means we double the thrust, but it doesn't double the ISP. Remember, ISP is an efficiency rating, and it doesn't add together like thrust. So if the ISP is the same between all our engines, we just use the single value. In this case, we'll use 320 seconds because we're in an atmosphere, so we're using the ISP value for sea level on Kerbin. So now we plug in all our values and we get 1,596 meters per second of delta V for this stage. Now, if you're interested in knowing how much time this stage should take to burn all its fuel, you can find that out by looking at our thrust to ISP to mass flow equations from earlier and solving for m dot. That will tell you how much mass will be chewed up for each second, and you need only compare that against your fuel mass with simple division to see how long it should take. You can also convert that mass to actual units of fuel if you want to find out what the mass per unit of fuel or oxidizer is. Either way, calculating the fuel mass flow is going to be useful if you want to do a second-by-second calculations of your spacecraft descent through an atmosphere, if you're someone keen enough to build spreadsheets for that kind of prediction. Now, stage 3 is the radial boosters. We know that 1596 meters per second isn't going to be enough to get to altitude, because we've seen the numbers for drag in the last 2 episodes. So we need more power! Or not. We need more delta V. It's not really the same thing. So we'll add on a third stage of some radial boosters to give some extra. Each booster is going to carry 50% more fuel than stage 2, and we're going to put on dual aerospike engines, which have a nice high ISP, both in vacuum, and they're unique in the stock lineup in that they lose only a fraction of a percent of ISP in the atmosphere, as opposed to the 15 to 20% or greater reduction seen by most other motors. And we're going to make this into a parallel staging that's been dubbed as aspargus staging by the KSP community. With this kind, we're going to take the fuel from the stage and use the fuel lines to feed some of it into the tanks for stage 2, so that both stage 3 aerospikes and the stage 2 LVT-45s can fire, but the stage 2 tanks will stay full. And unlike serial staging, the LVT-45s from the main lift stage are actually doing something useful. They aren't just dead weight. But this time we now have a mix of engines, and more importantly they have a mix of ISP values. So we need to find a way to combine them. So calculating the overall ISP for mixed engines is trick 5. Now some places may recommend using a thrust weighted average, however that isn't consistent with the math. So here's a mathematical proof which looks scary, but will eventually tell us that we need to use a m-dot weighted average instead. You can ignore this part if you don't care why it's right, and just skip ahead to the just use it portion. In a nutshell, we need the total thrust for all the engines that are going to be running, and we need the total mass flow for all those engines. These are just a couple of tidy sums which would give us the combined ISP for the stage. So adding the force of thrust is pretty straightforward. But instead of adding up the m-dot values for each engine, we can substitute the same equation for m-dot equals force of thrust over g-naught times ISP for each engine. Now if we do it that way, the g-naughts cancel out, and we have the total thrust at the top, and then the divisor is the sum of the quotients for each engine type of thrust over ISP. To apply this to our rocket, we plug in our various numbers. 1100 kilonewtons thrust total for all 6 engines, divided by the sum of 400 kilonewtons over 320 seconds for the 2 LVT-45s, and 700 kilonewtons over 388 seconds for the 4 aerospikes, and we end up with a blended ISP value of 360.2 seconds. Now that we have our ISP, we can total up the rest of the stage, and again all the previous stages are counted as payload, but we'll only be using the 24 tons of fuel in this stage for the delta V, nothing from stage 2. And our equation answers back to us with a respectable 2066 meters per second. Now, a quick safety note. I'm content to use the atmospheric ISP values for sea level for this equation, but remember, as the spacecraft descends, the ISP is going to improve, especially for the LVT-45s. That means that this rocket will actually end up with more delta V than we're showing here. You could get a closer answer by fudging or interpolating a median value for the ISP somewhere between sea level and vacuum, but I'm content with using the one ISP value for sea level since it builds in a safety factor by underestimating the capability of the rocket. I'd rather overbuild a rocket that will do more than I expect than have an underperforming rocket that gives me unpleasant surprises when it runs out of fuel halfway into orbit. But that's just me. Because these boosters are going to do most of their work in the lower atmosphere where the air's thick, they're also going to feature some winglets for aerodynamic control. That allows us to save our RCS for once we get higher up in the atmosphere or into vacuum, but it also allows us to dump the mass as soon as possible. So that should about do, and I'll just list the summary information for all the stages. At the end, we want to add up the delta V for all the stages, and we end up with 5,540 meters per second altogether. That should be enough for orbit. We'll name it Kerbal Space Lift, TAC Light, Garnet Mark 1, and we'll get it ready for launch. And I'll also rotate the pod to the east for takeoff so we can pitch over instead of yawing over. I don't really like flying sideways. I prefer to start out pointing in the right direction. Again, just me.
Hold count. RCS off. SAS off. Go flight. Roger. Checklist complete. Continue count. 10, 9, staging set. 8, 7, stage. Continue 6, count. 5, 4, 3, 2, 1. Mark. Total set. SAS set. Lift off. Clear the tower.
Okay, so now that we know what delta V the spacecraft has, let's talk about how we can estimate what it actually needs for orbit. This is actually a little backwards. You would usually check what the mission needs first, and then build a ship to those requirements. I'm showing it in this order because then we can fly the mission while we're talking about the math. This also isn't an exact or approved method of determining delta V requirements for ascent from an atmosphere. It's a discussion of the factors involved and what I've been doing to try and estimate them. As such, the usual disclaimer applies if your mileage may vary, and I'm sure that anyone who actually does know what they're doing with this math would probably cringe at what I'm about to do. You have been warned. So as we saw in the last two episodes, 1 TAC 2 Alpha and Bravo on gravity drag and atmospheric drag, we have a bunch of delta V values of what it would take to launch a spacecraft into orbit in yellow, and what it might lose to gravity in red, and what it would lose to air resistance in blue. All of these total up to 4,318 meters per second if we hit the worst case and had to overcome all of these exactly. I highly doubt that the actual numbers are this severe, but it gives a worst case, or at least an idea of the scope that we're dealing with. The actual air component is maybe half, and the altitude portion is probably a lot less because we need to get to a pretty high altitude before we can even start accelerating for that. And by that time, it's not likely that we'll need nearly that much, since the calculation's from 0 meters. So it's probably closer to 2,500 to 3,000 meters per second. But again, you can't go far wrong if you prepare for the worst case. Now that we've figured the up part out, we need to look at how much lateral velocity we need to reach orbit. And that takes us to tangential velocity, or VT. Now, tangential acceleration you might also hear referred to as centripidal force, and it has to do with the effect of objects moving in a circle, where the faster they move, the more they seem to want to fly away from the center. Kind of like spinning a cork on the end of a string, where the faster it goes, the less the string sags. And if you let go of the string, make sure it's not near anyone's fine china. So we see it in two forms depending on what you want to calculate. The tangential force, or Ft, equal to mass times velocity squared over r. Now the square of the velocity here isn't the overall velocity, it's only the velocity that is tangent to the center of the circle, or the planet, since it's a rocket science thing. Vertical motion doesn't count, only the horizontal. And of course r would be your altitude plus the radius of the planet. And since this is a force, we can put the F equals ma alongside it, and cancel out the mass terms to find that the tangential acceleration, regardless of mass, is equal to v squared over r. So just to illustrate what's going on, the object wants to carry on in the direction of the VT arrow in green, but it gets pulled towards the center by some other force, in this case gravity. But instead of being pulled all the way to the ground like an object that was just hovering, the object has an AT component that basically reduces the effect of gravity. We have another diagram showing the difference in closer detail, where the object is just hovering on the green line, it would fall straight down to gravity to some altitude shown by the blue dotted line. But another object moving at speed vt along the green arrow wants to carry on in a straight line, but alas is still pulled towards the center by gravity, but it doesn't get as far as the blue line. So the effective gravity gf is equal to g minus the at. So how cool is this? This means that if we're going to do a second-by-second calculations of the effects on the rocket, this tangential acceleration can be factored in to reduce the effective gravity on the rocket. That also means that in spreadsheets and in flight, the sooner that we can gain horizontal velocity, the less gravity drag we'll have to deal with. Now as we increase the VT, we can actually reduce the effective gravity to 0. So the object continues to be pulled by gravity but travels along the green path, not actually changing altitude at all. At that stage it has become an orbit, where our Kerbals are falling so fast that they miss the ground entirely.
Total set.
So that point where Vt is high enough that the tangential acceleration is equal to the acceleration due to gravity, we've reached VO, or orbital velocity. So there's a handy and simple proof around that takes the force of our tangential velocity and the other equation for force of gravity and makes them equal. When what we see is that the mass of our spacecraft, small m, cancels out, as does one of the radius terms. And we can take the big M mass of the planet with the gravitational constant and just refer to our previously saved spreadsheet values for the gravitational parameter. And what we get at the end is that our orbital velocity is just the square root of the gravitational parameter divided by the radius between the center of the planet and the spacecraft.
Go for stage.
So for our parking orbit, we can find the orbital velocity by taking the square root of our gravitational parameter for Kerbin divided by the radius, which is Kerbin's 600 kilometers plus 80 for the altitude, and we get 2,279 meters per second, which if we were on exactly that speed, exactly along the horizon, with no vertical velocity, at exactly 80,000 meters above sea level, we would be in pretty much a perfect circular orbit. Now it's not going to be exact, but it gives us a target. So long as we reach that lateral speed when we're at or above 80 kilometers, then we should end up with at least an elliptical orbit that keeps us at or above our parking orbit. So now that we have our required orbital velocity of 2,279 meters per second for our parking orbit at 80 kilometers of altitude, we can re-examine what we need to get into orbit. So with our first launch here, we've just thrusted straight up to gain altitude and then coast a little maybe until we get close to the apoapsis. And from there, we pitch over to the horizon and burn to build up our tangential velocity until it cancels out the gravity we need to get orbit. This is very inefficient, and going up and over we can see why. 6,597 meters per second. If our vertical numbers aren't overblown, our Garnet launcher is not going to make it. However, there are reasons to do this. Like Scott Manley's 100% reusable series right now, he's been going straight up with his lift stages so that they'll come straight back down near KSC for refueling. And you may notice while watching his videos that they've been consistently and progressively landing to the west for the most part.
Continue count.
Now, we're going to do a second launch with the same design, and this time we'll make use of a gravity turn.
4, 3, 2, 1, mark. Lift off. Clear the tower.
Since we've already seen how our sideways velocity can start reducing our gravity drag, it behooves us to start the gravity turn as soon as possible. And if we're looking at an airless body like the Mun, we could do that. However, on Kerbin we have an atmosphere to contend with, so it's more advantageous to go straight up for at least a little while, to get out of the soup as quickly as possible, and then start the gravity turn. As we saw in the air drag episode, that point is where our terminal velocity starts going up faster than the spacecraft is able to accelerate. So currently just about any ship can be ready for full throttle and a gravity turn at about 10 to 12 kilometers. That may change in 0.19 or 20, depending on what they do to the aerodynamic model. I am hoping they get rid of the instantaneous mass scaling to make it more realistic. But when that happens, ships are going to be a lot more variable, and we won't be able to use one terminal velocity chart for everybody.
Stage clear. Pitch over. Roger, stage.
I kept hearing gravity turn bandied about, but it wasn't overly intuitive what was meant by it. And basically, it's just a technique of using gravity to turn the trajectory of the rocket towards where we want it, So for example, we're trying to build tangential velocity. We can burn at an angle sort of up and a little sideways, and then gravity will act to change the trajectory closer to the horizon, which is more where we want it. Anyways, looking again at our delta V requirements, it should occur to anyone who's heard of Pythagoras that the shortest distance between two vectors like this is a straight line. So instead of up and over, why not go diagonally? And if we use the handy dandy Pythagoras theorem on this, which I'm not going to dignify with a sample as it should be known, we get 4,882 meters per second of delta V. If you really don't know about Pythagoras, apparently he was a character too. Vihard has a great video about it that I'd suggest watching just for fun. I'll leave a link for it in the video description.
Throttle down. Stand by. Roger.
Now again, this isn't very precise, and I have no idea if it'll actually bear out for other planets, but the calculation we get here is similar to the 45 to 4700 meters per second that is on most Kerbal delta V maps. And now I hear the screaming. What? There's just a map that tells us what the delta V is? What are we doing all this math for then? So yes, there are a couple maps sculling about if you haven't seen them yet, but sometimes they get out of date. The devs tend to add new planets or modify old ones, so it's possible for things like this to change.
Roger.
Like it most certainly will once the air drag model gets its overhaul in 0.19 and 2.0, and possibly beyond. So it's useful to know how to adapt to these changes and make the calculations ourselves. Also, the overall intention that the devs have for KSP at the moment is towards eventually having procedurally generated planets. That means a bunch of planets in your game, and your game alone, with no one else to put up a wiki about how much delta V is needed to take off from your particular world.
Roger. Continue burn. Throttle set. Nico.
Okay, now that we have Launch 1 and 2 in orbit, we can check their fuel and see what they have left, and see approximately how much they used getting up there. It's pretty easy to see how much of a difference it made to use the gravity turn in Launch 2 with just 4,282 meters per second delta V, as opposed to Launch 1 going up and over with 4,613 meters per second. Now, a word of caution, neither of these values is accurate. It's just an estimate based on the original delta V calculation for the rocket. But remember, we used a sea level ISP for the main lift stage and boosters, and the ISP would have gone up with the boosters and generated more delta V overall than we calculated. Now if it was an airless world where we had a constant vacuum ISP value, we'd be golden. But with an atmosphere, we'd have to go back and pretty much chart out the entire flight or something. There's also a flaw in this particular rocket design. If you notice, the boosters ran out of fuel on 2 of the engines before the other 2. This has to do with the way I set up the fuel feed lines for the aspargus staging. The upshot, the ship still achieved its mission even though something wasn't working right. Downside, it will muck up our calculations for the period of time when we were only running on 2 aerospikes. So guess which way our ISP went when that happened. So the Kerbal Space Center is going to spend the next little while trying to get the Garnet launchers down. This will allow them to test the effectiveness of the Separatrons for deorbiting the insertion stage, as well as the parachutes for a soft touchdown. Just for fun, if you want to confirm the delta V calculations, see how much delta V would be given to a spent insertion stage by the Separatrons. You'll need the mass of the dry stage, no payload since it would have been deployed, and no main engine fuel. And we'll see which way you go with the RCS propellant.
On my mark in 3, 2, 1, mark.
The other thing you can try is calculating the orbital velocity required for the MUN at a parking orbit of 4,000 meters. I'll try to remember to dig up the answers and put them at the beginning of the next video so you can see how you did. So that about wraps up this rather lengthy episode of Krash Test Kerbals. We've seen why launching straight up and down will have search parties heading west. We now know all about specific impulse and how it affects our burn times, our units of fuel per second, and mass reduction. We've seen how to calculate an overall ISP value for ships with mixed ISP engines. We've been able to put all that together to calculate the delta V for our stages and the spacecraft overall, both for serial and aspargus staging. We should at least have an idea what delta V means now, and why it's the real measure of the range or capability of our craft, rather than acceleration or a distance range as we may be used to with terrestrial transportation. We've also introduced tangential velocity and how our lateral motion can reduce our gravity drag. We know how to calculate orbital velocity and how to burn for that mark in case we don't have time to meddle around with the maneuver nodes. We've got a few numbers and equations in our pocket to start analyzing the delta V requirements for liftoff or descent on any world we care to visit. We've introduced the gravity turn during ascents and how transitioning to horizontal flight sooner can reduce our delta V requirements. And we have all the bits and pieces we could ever need to build a spreadsheet to get finer estimates of a second-by-second ascent or descent, as well as the overall one-time calculations to evaluate some capabilities.
Deploy chutes. Chutes deployed.
And I've learned that if I'm going to put this much stuff into a video, there's no way I'm going to be able to stick with a weekly or even bi-weekly schedule. In our next video, I intend to start looking at everything we could possibly need to know about orbits, so that will take a bit of time to put together as well.
Chutes open. Possible malfunction. Confirm. Confirm structural failure.
Apparently we have another flaw in this design. The force of the parachutes is ripping the rest of the rocket apart. When we design the Mark II, we'll see if mounting the parachutes lower down, perhaps the first fuel tank or so, will alleviate this. Of course, this also might be just due to the large reserves of unspent fuel that was left in the tanks, so there's a lot more momentum yanking at the nose cone adapter than we would expect to see normally.
Splashdown. Solid contact.
So thanks for watching, and if you found this in any way helpful, a thumbs up, comment, or share is always appreciated. Tell your friends to come for the concepts and stay for the math. This has been Purple Target at Crash and Learn. Peace out.